Find the particular solution for the differential equation y double prime plus 2y prime minus y equals 10. So to find the particular solution, we first need to find our homogeneous solution, where we take y double prime plus 2y prime minus y and set that equal to 0. And our auxiliary equation would find our roots, where r equals the amount of derivatives being taken. So y double prime is r squared plus 2r minus 1, since the coefficient of no derivatives is just 1, equals 0. And unfortunately, we need to do our quadratic formula to solve this, and a equals 1, b equals 2, and since b is an even number, we can take the b prime, which is just b over 2, which equals 1, and c equals negative 1. We can use our shortcut quadratic formula, minus b prime plus minus square root of b prime squared minus ac over a. You can use the original quadratic if you want. This is a little faster. And we know that this equals minus 1 plus minus square root of 1 squared is 1 minus ac, 1 times negative 1 over 1. And I'll just leave that out. So this equals minus 1 plus minus square root of 1 minus negative 1, which is just plus 1. So 1 plus 1 is 2. And we have our homogeneous roots. Our h equals minus 1 plus minus square root of 2. And as a quick side note, y homogeneous equals c1 e to the negative 1 plus rad 2 times t plus c2 e to the negative 1 minus rad 2 times t. And we need to know this in order to find our particular solution, particularly our h. So for y particular, the general form of analysis is ay double prime plus by prime plus cy equals c times t to the m e to the r particular t, where a, b, c, and capital C are constants, t is the independent variable to the power of m, and e is taken to the power of a particular root times t. And once we find some of these variables, we can start evaluating the undetermined coefficients. So upon quick inspection, m equals 0 since there is no independent variable on the right-hand side, and rp also equals 0 since there is no e term, which is important since rp does not equal rh. rh is this whole term. So we can conclude that s equals 0. And now y particular, and we can take it a variable t if you want, equals t to the s times a decreasing polynomial of degree m, so a sub m times t to the m plus a sub m minus 1, t to the m minus 1, plus so on and so forth until you hit ace of 1 of t plus ace of 0, times e to the r particular t. And as we said before, s equals 0 in the case that there's a repeated root, but we can get rid of that since t to the 0 is just 1. So y particular of t equals t to the power of 0, and we also said m is 0, so we can get rid of all m equals non-zero terms down to ace of 0. And we can just also take e to the 0 as rp equals 0. So y particular of t equals ace of 0. That's it. And the plan is to take 2 more derivatives of this term. So that we can plug it back into the original equation. So taking a derivative of a constant, ace of 0, is just 0, and doing another derivative won't change anything. So we can plug that in to the equation y double prime minus 2y prime minus y equals 10, which turns out to be 0 for y double prime, minus 2 times y single prime, which is again 0, minus y, ace of 0, equals 10. So we know that negative ace of 0 equals 10. This is a very easy and straightforward example. It can get really messy, especially once you have trig functions. So divide by negative 1. Our one and only constant equals negative 10, which means that yp of t equals negative 10. And that is our solution to this problem. I'll go ahead and also write the general solution, which isn't explicitly asked for, which just equals yh plus yp. And that's c1 e to the negative 1 plus rad 2t plus c2 e to the negative 1 minus rad 2t. All you have to do is just subtract 10 from that, and we have our general solution. This problem only asks for this portion though. I hope this helped you. If it did, please like and subscribe, and I'll see you in the next video.